This is section 1.4, velocity, uh, out of Pearson. All right, we've talked about linear displacement. Now we need to talk about velocity. And really quickly, velocity is the change in displacement divided by time. So how far did you move divided by the time it took you to move there? Okay, we're going to talk about velocity now. So down here at the bottom, we have speed equals distance traveled in a given time interval. Okay, so we take our distance and divide it by the time. That's like miles per hour. That's your speed. And here in the slideshow, we got a car and a bicycle, and we see their positions as a function of time. So after 1 second, the car has traveled 40 feet and the bicycle has traveled 20. Okay. Then after another second, the car travels another 40 feet to a total displacement of 80. And then it again moves 20 feet after 3 seconds. So we can see, so in 3 seconds, the car has moved 120 feet and the bicycle has moved 60 feet. Okay. So we can calculate the velocity and the speed for each of those. Just take the speed divided by the time. So we can see that the bike is traveling at 20 feet per second, right? 20 feet per second, and the car is going at 40 feet per second. Jane walks to the right at a constant rate, moving 3 meters in 3 seconds. At t equals 0, she passes the x equals 1 mark. Draw her motion diagram for t equals -1 to 4 seconds, where he went. Okay. Jane walks to the right at a constant rate, moving 3 meters in 3 seconds. Okay, so we'll say Bulbasaur, he is moving. We'll put this is 3 meters. Okay, so let's say this is 3 meters in 3 seconds. So his displacement is 3 meters, and his time is going to be 3 seconds. So if we want to get his velocity, that is going to be delta x over delta t, which is going to give me 3 meters divided by 3 seconds. And so 3 divided by 3 is 1 meter per second. And we need a of direction. So he's going to the right, okay, at 1 meter per second. Okay, so at t equals 0, Bulbasaur passes the x equals 1 meter mark. So right here, okay, this is t equals 0. Okay, and then draw her motion diagram from -1 up to 4 seconds. Okay, so okay, this is 3, 2, 1. This is 0, 1, 2, and at t equals -1. Okay, so at t equals 0, she's a 1. At -1, so this would be t equals -1, then we're at 0. Okay, so here's my motion diagram. All right, I'm going to draw it down here because we're getting a little crowded up here. Okay, so here, this is at t equals -1. Then at t equals 0. So this is t equals 0. So this is our position: 1 meter, 0, 2 meters, and then 3 meters. And at 4 seconds is -1, 0, 1, 2, 3, and then 4. So this is I guess this is our motion diagram. Let's see if that is what they were going for. I think it is. Okay, so yeah, we did it. Okay, so speed measures, draw her motion diagram. I think we did it. Okay, so here's another motion diagram. Velocity and speed. Okay, so speed measures only how fast an object moves, but velocity tells us both the speed and the direction. That's really the key difference, right? What direction is it moving? Okay, so here we've got bike one and bike two. Bike two is going to the left. Okay, so it's moving in the negative x direction. Okay, the velocity is called the average velocity, which means basically if we know the velocity at 2 points, okay, we can compute the average velocity. We don't know what happened in between, but we basically just take those 2 points and we divide it by the time it took you to get there. That's your average velocity. Okay, let's check out this example of an albatross. Albatross are seabirds that spend most of their lives flying over the ocean looking for food. With a stiff tailwind, an albatross can fly at high speeds. Satellite data on particular speedy albatrosses show it 60 miles east of its roost at 3 p.m. Okay, so here let's draw our albatross. Okay, here's our albatross. And yeah, so here's our albatross. They have really big, huge wingspans. Okay, here's our beautiful, majestic albatross there. Yes. Okay, but remember, we're going to make a model of him, so he's going to be Mr. Albatross is going to be this point particle. So it says at 3 p.m. So this is 3 p.m. Where was Mr. Albatross? Okay, his nest is over here. There's his albatross nest. Okay. And at 3 p.m., he was 60 miles east of his nest. Okay, so this will be 1, 2, 3, 4, 5, 6. Oh, that was lucky. Okay, so this is 60 miles. Okay. It's 60 miles, and then at 3:15, Mr. Albatross, he moved over here. This is 3:15 right there, 3:15. Now Mr. Albatross is 80 miles away. There's 80 miles. Okay. There's Mr. Albatross. Oh, you can't see it. Oh my gosh. Okay. So at 3 p.m., Mr. Albatross was 60 miles east, and at 3:15, he was 80 miles east. Okay. What is its velocity? Well, okay, so right here, we can see that Mr. Albatross, he traveled 20 miles. 20 20 miles. We're going to keep this in miles. We'll probably do miles per hour. Okay. Because that I think is going to be easy. I don't want to convert this into meters right now. Okay, so this was 15 minutes or 1/4 of an hour. So this was, we'll say delta T equals, this will be 0.25 hours, right? Yeah, 0.25 hours. That's good. Okay, so then we're going to say, all right, what is his velocity? It's 20 miles divided by 0.25 hours. Okay, that's I think this is the easiest way to do this problem. So I'm going to plug this in. I'm going to say 20 divided by 0.25. That gives me, oh man, this thing is trucking. Mr. Albatross is flying at 80 miles per hour. Whoa, that is one speedy albatross. Oh my goodness. That albatross is flying. Literally flying. 80 miles an hour. And yes, indeed, it is. Okay, so they did it the same way in the presentation. 20 miles per hour divided by 0.25 hours. That gives us 80 miles per hour. Okay, assess. Velocity is positive, which makes sense because the figure shows the motion to the right. Yes, traveling to the east. Okay. Here's another example problem. At t equals 12 seconds, Frank is at x equals 25 meters. 5 seconds later, he's at 20 meters. What is Frank's velocity? What do we do? Draw a picture. Of course, we draw a picture. We should always draw pictures. Okay. So we'll make Frank. There's Frank. Frank is the purple dot. Here's the actual man, Frank. There we go. My friend Frank. Okay. He is at 25 meters. Okay, so let's say this is 20, 15. Yeah, these are each. Okay, so it's 10. Okay, so right here, this is x equals 0, and here's 25 meters. Okay, that's 25 meters. Here's our axis. Okay, I'm drawing my axis right here. Always draw a picture. Please, please draw pictures. Okay. Um, and then at 5 seconds later, so we'll say this is t equals 12 seconds. Okay. At 5 seconds later is at 20 meters. Oh, he went back this way. Okay, so Frank moved this way. He went from 25 meters to 20 meters in 5 seconds. Okay, so what was the total distance that he traveled? Um, okay, the information that t equals 12 seconds is extraneous. Yeah, it doesn't matter. Okay. Let's figure this out. Okay. So he went a total of five meters in the negative direction. Okay, so we start off our final position. So XF minus X initial divided by T final minus T initial. This is going to equal our velocity. Okay, so this is what we're doing. We're just going to plug in our information. Now, it tells us that this took 5 seconds. Okay, so we don't care that it started at 12 seconds because it says 5 seconds later. So we're just on the bottom here. We're just going to put 5 seconds. Okay, and then we had 25. Oh yeah, no, our final position was 20 meters minus our initial position, which is 25 meters. Okay, so now we've got our velocity here. Our velocity is going to be 25 meters divided by 5 seconds. So 25 divided by 5 that's going to give us 5 meters per second, and it's going to be negative. Okay, so we got our velocity. All right, that was a good example problem. We know how to calculate velocity now. Jenny runs. Oh, there we go. I'll go back for a second. All right. Yes. Let's do another one. We're almost done with this section. Jenny runs 1 mile to the northeast and then 1 mile south. Graphically find her net displacement. Okay, so now we're dealing with northeast and then south. Okay, so we're going to draw a picture here. Show on the screen. Okay. So here is Jenny. She's gonna be a green dot. To make it a model of Jenny. Here's Jenny. Yeah. Okay. Jenny's the green dot. And let's see. She goes to the northeast. She travels 1 mile. And we'll say, okay, she goes 1 mile this way. We'll call that 1 mile. Okay. And then Jenny goes south 1 mile. Okay, so this is 1 mile. Okay, we need to do the same distance south, but I did the diagonal here, so she's gonna go. Okay, so she goes about there. That's also 1 mile. Okay. Graphically find her net displacement. Okay, well, she's going to end up down here somewhere. Okay, so at first she went 45 degrees, right? Because she went northeast up here. She ended up right here. Okay, that is, and then she went down over here, okay, 1 mile, the same distance here. So she's going to end up about there. Okay, so that is her net displacement. We drew this, this is delta R. We'll call it her net displacement. That's R. Okay, it's right there. Example problem. Oh, wait, we did this one. Okay. All right, so that's the end of the section.